gravity can be this are several, depending on the point of view. I find that the most compelling one are regarding the thermodynamic, the so-called approaches that are showing the thermodynamical aspect of space-time, in particular the approach at Jacobson, where you find that you can retrieve the Einstein equation as equations of state with a very general argument, starting basically by the equivalence principle and from using local Lorentz invariance and the quantum field theory on a locally flat patch of space-time. And I find very interesting the fact that there are also non-equilibrium terms, what you would call heat fluxes, and these heat fluxes are related basically to the gravitational degrees of freedom. So, for example, the Hartley-Hawking tidal heating, the dissipation, the gravitational wave, it looks like an heat flux in this approach. And if you have an heat flux, if something can be heated, it has microstructure somehow. So this is something going in that direction. Now, regarding, if we want to discuss about emergent gravity, we should start, first of all, agreeing what we expect to emerge. Should we emerge basically just the Einstein equation? Do we want to have, are we willing to contemplate more radical ideas like the fact that also quantum mechanics can be an emergent phenomenon as we know it? So we have in a certain sense a hierarchy of issues that we need to tackle. And I also want to stress that there are many approaches nowadays that can go under a general label of general ideas that you could call emergent gravity scenario, but they are very different among them. And you cannot, in a certain sense, at the moment, give a single point of view regarding what is emergent gravity. So as I said in this talk, I'm trying to take a very down-to-earth point of view. I'm taking a specific class of models, the so-called analogous models of gravity, based on condensed matter system, which simulated some of the salient features of gravity and field theory on a curved background. And I'm trying to use this as a kind of learning tool, just to see what they are suggesting about, in this particular set of ideas, what kind of phenomenology you would expect if indeed the reality is emerging. Now, let me start with immediately with a specific analog model of gravity, which has many interesting features, and this is basically standard Bose-Einstein condensate. So standard Bose-Einstein condensate are described by a many-body Hamiltonian, and we are working a dilute condensate approach where you can basically put just this interaction there. And what you generally do to treat this system is you go to a mean field approximation. So you have the so-called wave function of the condensate, which is a classical object, and you have the quantum excitation that are basically the operators which are creating and destroy atoms. Let me just make immediately a comment that the ground state of the condensate is the ground state where you don't have waves on the condensate, which is not the ground state for the atom. Okay? This will become important later. Now what you do, you insert this mean field approach ansatz in the equation, and you get a couple of equations, one for the background and one for the excitation dynamics. And then you see you have several terms here that are basically implementing the back reaction of the quantum excitation, for example, on the background. Let me ignore them for a moment. And let me also stress that you see for the excitation you have an equation that is clearly mixing this object is related to the distraction operator, this creation operator. And somehow you immediately understand that the propagating particles are not the atoms here. You have to do a Bogoliubov transformation to get to what are called the phons, or the quasi-particle of the condensate. So what you can do is that you use this answer here. This is a perturbation in the density, and this is a perturbation in the phase. And you can rewrite the equation, neglecting the back reaction term, as a set of basically hydrodynamic equations. This is no surprise, because all in all, apart from the nonlinear term, you were dealing with a Schrödinger equation. You know really that you can cast it in a hydrodynamical form. Let me ignore for the moment this differential operator, which is anyway suppressed by h squared. Then what I do, I can take these two linearized equations, put them together to get the second order equation for the perturbation in the phase. And you see what happens? We should find something which is the Lambertian in a curved space-time of this operator. Okay? This object is basically the phonons, And they propagate on a background which is normally called the acoustic geometry. And you see that the speed of light is replaced by the speed of sound, which is a function of the microscopic quantity. So what we have found is that basically answering to the question, if I look at phonons on a Bose-Einstein condensate, how do they propagate? They propagate like massless particle on a curved background, where the curvature of the background is due by the background velocity and density. Okay? Density times zero. So I basically have a simulation here of quantum field theory in a curved space-time. No more than that. I don't have the Einstein equation. Okay? And now people have been playing for a long time. I mean, this is basically a theorem. Whenever you have a superfluid in viscous and in rotational, you can do this by linearized perturbation. And people, for example, now is producing in laboratory analog black holes because this metric can simulate a black hole. And basically what you do then is try to get the analog of Hawking radiation. And what people is studying is correlation of the Hawking quanta as a way to detect them in a laboratory. And let's say the black hole has been done for the first time last year. And basically now we are approaching the point in which we will see the analog of the Hawking radiation. But it's not what I want to talk about. I want to start talking, for example, about the theory of the phonons, the effective field theory for the phonons. And the first remark, which is interesting to make, is that this effective field theory is a particular property. You see, if this is the phononic operator, and these are the operators related to atoms, given that there is a Bogoliubov transformation, in order to write this one as a function of the atomic one, you have basically this form. This is basically from this. And you see, basically you have a non-local transformation. It's not just a linear combination. It's due to the fact that there is a Bogoliubov transformation relating the two objects. Now, what is the implication of this? That there is some non-locality, and you can check that basically you realize when there is this non-locality, not when you look at just at phonons. The commutator of phonons is canonical. Not when you just look at atoms. The commutator of atoms is canonical. But when you look at, for example, commutator of this object with this object, then you get something strange. And what is happening is basically this, that when you look at the interaction, the voltamental vertex in the Lagrangian is a 4 atoms interaction. There is no 4 phonon interaction at the fundamental level. So when you try to do a scattering of phonons, what is happening is that if the scattering is sufficiently high energy, then some local effect should show up due to the fact that you need at some point to convert to the atoms. You always need to do that, but the effect is relevant only if the energy are sufficiently high. And the scale, which is important, is this one. It's called the Hilling length, and it's basically the scale of coherence of the Bose-Einstein condensate if you think of it as a superfluid. We will see that this Hilling length is basically also what rules Lorentz violation in the phononic dispersion relation. So first point is that there is some kind of non-locality in the theory of collective excitation, because the effective field theory of collective excitation at some high energy will see that these are collective excitation related by Bogoliubov transformation to the constituents, and will show this non-locality. The other interesting point is that if you don't neglect the differential operator D2 that I neglected in order to get to the acoustic geometry, then what you get a modified dispersion relation which has an higher order correction. This is the so-called Bogoliubov dispersion relation. It's something well known. Is experimentally, they play with phonons in Bose-Einstein. They know that this is something that we know is actually implemented in nature. It's not just. And you see, this is showing you that naturally in this system there is ultraviolet Lorentz breaking. Okay? And it's obvious that there should be, and they should be superluminal. Why? Because the underlying theory is basically non-relativistic. So when you go up with the energy, at some point you should see that the apparent relativity group, some acoustic Lorentz group, should be just an accidental symmetry that at high energy you lose, and you should have that the characteristics are basically going superluminal. There is no light cone at very high energy. Actually, if you take this dispersion relation and pump up the momentum, what is happening is that you get the non-relativistic. When this term is dominant on this one, you get basically E equal P square of 1, as it should be. Okay? But how much is generic the fact, for example, that we see Lorentz violation? Well, here it comes, in a certain sense, a matter of speculation, but you can argue in this way. First of all, there is a subtlety that needs to be fixed, that there isn't an identity between Lorentz violation and relativity violation. You can see this, for example, if you think of the derivation of special relativity alla Von-Ignatowski in an asymmetric way. Von-Ignatowski basically in 1911 showed that you don't need to start from the universality of the speed of light. You just base the derivation on some postulate about the nature of space-time. You start assuming the principle of relativity, then you assume isotropy and homogeneity, and precausality, which it means that if two colloquial events have a given time ordering in a system of reference, it must be the same time ordering in any system of reference. And putting all together, you get basically Lorentz transformation with a invariant speed, let's call it capital C, that then experiment tells you if it is the speed of light or is infinite, and then you get Galileo. Okay. In a sense, what is happening is that when you have the emergence of space-time, one of the things you may expect in general is that there is a breakdown at some point of homogeneity. Basically, an underlying assumption is that space-time looks the same at whatever scale you look at it. And of course, in this system, this is not true. But I want to stress that it's not obvious that what comes after is Galileo. Okay? For example, you can give up instead of isotropy, and we know that you can get a relativity group which is leaving invariant a Finsler geometry. That means a geometry that depends on the speed at a point, not just a point. Yes?
Yeah, maybe this is a detail not everybody is interested in, but what's logically the exact relationship between homogeneity and linearity?
Basically that you need, at some point, the fact that you assume homogeneity of the transformation, that tells you that it must be a linear transformation in the Von-Ignatowski theorem. So when you drop homogeneity, for example, you may think that you have no linear transformation. And if you drop also translation invariance, you can even have weird composition of momentum. And you know what this is saying? I don't know. I tried that, but it's not that easy. I tried also to give up isotropy and see if I can get a new relativity group with the same number of generators with Finsler geometry left invariant, but you always end up with less generators. Anyway. However, let me point another point, that if you want to do emergent gravity and you want to start with a manifold that has really some structure, basically you have the Weinberg-Witten theorem to face, which is telling you that this is really a vulgata, and really the gist is not the way it is written. But basically it's telling you that you cannot have an emergent spin-2 particle if you are starting from a world which is Lorentz invariant. Okay? More precisely, if you have gauge invariant currents or a covariantly conserved stress energy tensor. There are basically two ways out of it. Or you emerge everything at once. You have the fundamental constituent and you come up all of a sudden with everything, all the structure we know. Or you do emerge first a manifold, maybe flat space-time, with some primitive fields, and then this field basically generate for you the condensate, which is gravity, in the analogy which I just made. However, in that case, you have to pay the toll to break Lorentz invariance amount. But given the argument they made, it's not obvious that you need Lorentz violation, or you can have a new relativity group, for example, or just as you might reconstruct, we recently construct a system of relativistic Bose-Einstein, where the atoms are relativistic as well. This is a theoretically studied system, but not yet realized in a laboratory. Then you have a very strange things, because you have again, at low energy phonons on a curved background with acoustic Lorentz invariance. Then you have a transition phase at some energy where it looks like the dispersion relation is of the sort you just saw, the modified one. But then it just become again a fully relativistic dispersion relation with the c equal to the speed of light. And there is no gravity, there is just flat space. So it's like gravity switch off and you have a new relativity group. This is a different scenario from what we generally consider. So, okay, we have a Lorentz violation. It seems to be a very important ingredient in this emergent gravity scenario. Let's test it. We want to do phenomenology here, no? Well, people has done a lot of phenomenology of Lorentz violation. I was almost tempted to not put it, but I think that is worth mentioning, given that so far nobody has done a kind of picture of where we stand. The situation. The situation is that basically there are three main lines of research, three main frameworks that I'm simplifying, but this is more or less the situation. One is Lorentz symmetry violation, hardcore Lorentz symmetry violation, and treated it with an effective field theory. Then the effective field theory can be just made with a normalizable operator. This takes the name of minimal standard model extensions. Before it was just standard model extension, now it's accepted that this is the minimal one. And then, otherwise, you can add also non-renormalizable operator. All in all, if you accepted that to live with an effective field theory, why you should be renormalizing? Okay? The alternative with treating Lorentz violation is having models which do not have an effective field theory formulation, because there is some kind of hidden sector. It's basically the model of space-time foam that Nick and collaborator have been studying, and that he has nicely presented Monday. Finally, there is a completely alternative paradigm, which is the form of doubly spatial relativity, and this one basically is at the level where people are still trying to consistently implement it. The idea is that basically there is no, the relativity principle is still there. Simply you have given up some other assumption in the von Minkowski, if you like. This is my way of saying it. And somehow you have that you have to introduce new structure that are not traditional, from unknown competitive space-time, Finsler geometry. You can interpret it as a measurement theory. There is a lot of activity, but I would say it's still at the theoretical level, because once it is completely formed, it's difficult to cast solid constraints. So I will focus here for a moment on effective field theory with dimension 5 and higher Lorentz violation, and non-critical strings. So, first of all, let me review the situation with, I will just talk about QED, because there are also other constraints, but the time is limited. So QED, P-cube modification. In effective field theory, you have a birefringent photons, and basically the situation is the one you see here. And you see that the constraints are very strong, and they are all coming from a beloved object that has a very special status in my art, which is the Crab Nebula. The Crab Nebula basically is providing the best constraint nowadays, because we measure synchrotron radiation from the Crab Nebula. This synchrotron radiation is polarized. The birefringence of the photon is destroying very rapidly the polarization, because it is introducing a kind of Faraday rotation, if you like, which is rotating the polarization at different speed for different energy. And the other constraint, the one on the electrons, is coming from the fact that also electrons, the critical frequency for synchrotron radiation is very sensitive to this modification of the dispersion relation, and you can reconstruct the synchrotron spectrum, and you get very strong constraint also on the electron sector. These are the numbers. I don't know if you can read it. We are on the electrons at 10 to the minus 7, on the photons at 10 to the minus 11, roughly. Okay? For coefficient that naturally would be, we expect to be of order 1. So I would say this is very strongly constrained. We can go to the next order, but in order to do that, it's obvious that you need higher energy. And the higher energy are provided basically by ultra-high energy cosmic rays. And the basic reaction here is the GZK process, which is also the one which we use to constrain the proton and the pion sector. And the way you do constraints in QED is basically looking at the gamma higher production. It's a very important reaction in astrophysics, and this reaction, basically what it's doing is absorbing on the CMB most of the photons which are created by the absorption, the decay of the pi zero created in the GZK. Okay, so we have already bounds on how much photons can arrive on Earth, and you see there is a point. If you have Lorentz violation, you can show is a theorem that if a reaction has a lower threshold, then it can have an upper threshold. This is the space of all the possible states. This is there is an offset due to the background photon, and this is the dispersion relation of the photon, okay, of the high energy photon. You see, it can enter the the region of allowed solution, but it can also exit. That is what we call an upper threshold. And basically, if you allow the parameter to free have both sides, basically there is always an upper threshold when normally there was a lower threshold. So if you are above upper threshold, this reaction doesn't happen anymore, and we should be swamped, completely invaded by these ultra-high energy gamma rays. Not nice. And fortunately, we have bounds, and they have not been observed at LJ, but we know that there are very few. And this excludes all this part. Here is 10 to the minus 7, and here is 10 to the minus 7. Okay? But it's not yet a full constraint. All this part is allowed. In order to clearly close the game, we need to observe at least one of these photons. And you know why? Because these photons, if they can also do gamma decay, that means once you violate Lorentz invariance, you can have the basic vertex of QED, gamma, that goes in a plus and minus. You are taught that this is forbidden by energy conservation, but if I change the dispersion relation, it's not. And basically, if I observe one of these gamma ray, given that this reaction is ultra fast, what is happening is that they should propagate at any astrophysical distance. So if I observe one, then we close the game.
Unless it is superluminal, I suppose. Or
no, this is already included. I allow you both to superluminal. If it is superluminal, it's constrained by the upper threshold and this way. Actually, superluminal. No, it's superluminal. If the electron is not changed, you need a superluminal photon to decay in a plus and minus. Anyway, so this is the situation with effective field theory. However, as Daniel has nicely pointed out yesterday, there is a problem with effective field theory with Lorentz violation. And this problem is the so-called unnaturalness or naturalness problem. And it's a naturalness problem which is summarizing what, or giving my version, my vulgata of the problem is that basically you have radiative correction. Imagine that you just modified the photon and not the electron. The radiative correction will basically modify the propagator of the electron. And they would modify it, so even if you start with a photon, change it only at the p to the 4th, you get also p-square modification. That means in the limit speed for the electron. Basically, Lorentz violation has this bad habit to perforate on the renormalizable operator where we have very strong constraints. So, in a certain sense, you can constrain higher order Lorentz violation by looking at the lowest order. However, this mechanism applies also for other gravity, was discovered only 5 years later, rediscovered. And they basically find the same point. It's an interesting fact that things. But there is a possibility, and the possibility is that if there is another scale in the game, apart from Lorentz violation scale, and for example, people consider if you have a custodial symmetry that a priori forbids the renormalizable operators, and then might be broken, then you expect extra suppression term, which are order of powers of the higher this new scale over the Planck scale. This is what people are trying to do with supersymmetry, but it doesn't fully work. So the problem is not solved. And we have also tried to look at this from the point of view of Arnold's model, and there it seems that there is again some custodial symmetry protecting in a 2D seed, when now you have two kinds of forms, the system, but again it's not a proof that the problem is not there in nature. Finally, it's not clear how this mechanism would work in a system like the one I was telling you before, the relativistic Bose-Einstein, where you have Lorentz, transitions, Lorentz again.
So, Peter, when you say that it doesn't fully work, do you mean that they have not fully worked it out, or that there's actually some problem?
The problem is that what they worked out, they find not the kind of dispersion relation that I'm constraining. There is further suppression, which is ratio of the mass of every Planck. In their model, the QED with SUSY. And there is also the question that Daniel was pointing, that you may have arguments against using SUSY when there is Lorentz breaking, because they are relying also on the translation invariance.
So that's the point.
And then, but the point is,
forget about that.
Well, the point is that SUSY is not forbidding per se the dimension 5 operator. When it's broken, the dimension 5 operator, the p cube, gives you a p operator, which is not enough suppressed, as a coefficient which is not enough suppressed and would be already ruled out. You need to add the CPT invariance, go to the p to the 4th, then you get lambda SUSY over n Planck square, and that one is barely compatible with observation. if lambda SUSY does not get higher than 10 to the 14 electron volt, 10 to the 13, 14 electron volt. So it's very important if they find SUSY at the leg C before this kind of discussion, because if the scale of SUSY is too high, the suppression is not enough for being compatible with the constraints on renormalizable phase.
So let me understand, they have to impose this CPT invariance, and then the fourth order one is barely
then
there.
It's the first one you can construct,
yeah,
and when it's broken
and
SUSY.
it's barely there, and what's the scale that you were saying for SUSY? That
Well, let's say that you have that when it's broken, you get in front of the p square lambda SUSY or n plan square. This is 10 to the minus 15. Square is 10 to the minus 30. The current constraints are 10 to the minus 15 if you consider 10 to 10 TeV, lambda SUSY. And where the constraint is 10 to the minus 27. 3 order of magnitude of levels. Yeah.
it's almost about
Right. So then you may have another further argument to go and look at the theory which is beyond the effective field theory. And this is the theory that Nick has been playing with since many years. I'm now talking about the specific implementation of this theory, where basically you have these d particles which are recalling with photons. They are changing only photons and in a particular way without birefringence. You basically use all the constraints I showed you so far. And you also have that the energy conservation is modified with this coefficient, which is taking into account that some energy transfer can go to the particle. And I'm assuming that basically on average it's not zero, these transfers. And so this size is not on average zero. This is a flavor of the model that was basically published in 2001. Okay? If you adopt this model, you realize that the gamma-gamma going in the plus or minus is still there, because you can't apply this model to that reaction. You still have that there shouldn't be an upper threshold. Otherwise, the flux of photons shot up in the sky by high order of magnitude with respect to what you would expect, or the bounce of it. And then basically this is the constraint. The sum of these two coefficients should be less than 10 to the minus 12. So this model, I would say, is ruled out if it wouldn't be for the fact that we have some uncertainty on the Auger data, although recently there was a paper showing that the uncertainty in the Auger data are suppressing the expected photon flux by just 1 order of magnitude. This is a paper by Subir Sarkar, Andrew Taylor, and the third guy I don't remember at the moment, I apologize. And basically, so I think it's safe, the constraint I just gave you. Now, the last part, I'm going to discuss that you can do even more with a BC, and you can try to ask a question, like this. Okay, I have an emergent geometry, but I don't have an emergent Einstein equation. Can I get a gravitational equation? And then you say, okay, this is crazy because you have the ground equation is not relativistic. And then I say, okay, can I get something that looks like Poisson equation? So let me look at the gravitational potential associated with this effective geometry, the one experienced by the phonons. And then I look if the ground equation can be cast in as a background equation for this potential, this gravitational potential, and this if there's any normal force. So what we do is basically, first of all, there is a trick we need to play. We need to softly broach the U1 symmetry of the Bose-Einstein to give a mass to the gravity. We want to work with massive particles. And this can be done. It's just a technical problem. And then we want to see if we get something like this. This is the most general Poisson equation you can write with short-range gravity in a cosmological constant. So what you do perturbation. You realize that the perturbation in the acoustic geometry are basically density perturbation. You write an ansatz where you perturb slightly the background. You go in the weak field, static field approximation. You consider the field basically static, weak. And you try to you look at the non-relativistic Hamiltonian experienced by the phonons. So to identify which is playing the role of the gravitational potential. It is this object. It's a very long derivation that I'm making short in a sense, but this is the gist. At the end, you've identified what should play the game in this equation, what should be this guy. Okay? Now you want to see if this guy, looking at the equation I gave you for the background at the start, satisfy a sort of modified Poisson equation. You have a kind of complicated procedure. You have to keep the back reaction term of the atoms on the condensate, and this is what you find. You do get a modified Poisson equation. And this Poisson equation is characterized by a finite range for gravity, which is fixed by microscopic quantity. This is basically the Hillen length. And G Newton is a combination of the chemical potential, the coupling that you need to give the mass to the graviton, and so on. These are all microscopic objects. And finally, you have a cosmological constant. And this is very interesting. You get generically a cosmological constant, and where is coming from this cosmological constant? If you look at what it is, this cosmological constant is what is called by people in condensed matter the depletion factor. See, I told you at the start that in the condensate it is in the ground state for the phonons, not for the atoms. So when you put it, when you look at the ground state for the phonons, there are always a gas of atoms above the condensate. There is no perfect condensation as such. If the condensation is good, there is very few of these atoms. They are basically going like 1 over n, where n is the number of atoms in the condensate. These atoms are basically back-reacting. It's making a constant back reaction on the condensate, and this back reaction is what appears in the role of the cosmological constant in this analog gravitational equation. This is related, and this is a point that is interesting to make, to a general problem. You see, the general problem is that when you are dealing with this system, where you have a collective excitation in atoms, there is a true separation between the vacuum energy. You shouldn't compute it with a phonon effective Hamiltonian. Because if you do that, you get a huge answer. You put basically the Hilly length to the fourth Hamiltonian. This is what we do normally when we state the problem with, you put the cutoff of your effective field theory, you get the cutoff to the fourth, basically, as the scale of your cosmological constant. But the right way in this system to compute the vacuum energy is to take the Hamiltonian of the atoms and subtract basically the energy which is stored in the atoms which are in the condensate. And if you do that, you're left with the energy which is provided on the system by the atoms which are not in the condensate, which are basically is related to the expectation value, the 2-point expectation value of the atomic operator. So this is an example where in this system the effective field theory intuition fails. Because this is the effective field theory intuition, and here you need really to know the microscopic system to do the exact calculations. Otherwise you don't explain them. So these are the lessons from Bose-Einstein. And then I have 5 minutes. Can I use a bit more? Because I want to discuss different variants. 3. Give me some more, because there is the different variants is worth discussing. So, what we have learned? We have learned this, that the effective field theory of the collective excitation has this high energy non-locality, which may be important, I don't know, the cold evaporation. Then we have learned that there is this failure of the VFT intuition for some questions, not all the questions. VFT is good for many questions, but not for all. And we have learned that there is generically in this system Lorentz vibration. Okay? Now, what about the background independence? I'm going to be a bit sloppy for the reason of time between different variants and background independence. I know that there is Domenico there, and you know that I should be careful on that, correctly so, but I won't. So, my point is basically this. Do we expect that also the different field invariant should emerge? Because this system, of course, doesn't have different variants. My answer is that the different variant seems to be tightly linked to the thermodynamical aspects of gravity, because the nether charge associated to different variants is strictly associated with the Becker-Stenokin entropy. So my personal guess is that different variants cannot be fundamental if you want to explain the thermodynamical aspects of gravity as a byproduct of the fact that gravity is emerging. So following this logic, I would expect that different variant should be given up. So there is a whole phenomenology that we could try to do, which is trying to insert an effective field theory way, Lorentz different terms, and try to constrain them. This has been done, to my knowledge, by Donahue as the first attempt in this direction, but it was basically adding a coordinate-dependent term, and I feel a bit uncomfortable. I would prefer to add background structure, in a sense, add fields which are non-dynamical, and try to put constraint on that. I don't know if this can be done. It's just I'm throwing an idea. I haven't done anything in this direction. Now, given that my time is end, the last exercises I wanted to show you is that in principle you can do better than what we have done with the Bose-Einstein condensate, inventing a model on your own inspired by the Bose-Einstein condensate. So let me give you the gist of what we have done. We have taken basically some k-essence-like field. Do you know what k-essence? You don't for sure. But you know what k-essence-like fields are? They're basically fields which have a non-canonical kinetic term. It can be some arbitrary function, it's not the standard one. And here, xi are the standard kinetic term. Okay? And put them on a Euclidean spacetime. They do not even times. What you can show is that if you select in a specific background solution around which the two-perturbation theory, you can show that the perturbation propagate on an effective geometry, and here is crucial the fact that the kinetic term are not traditional k-essence line. An effective geometry which is not the Euclidean one, and you can even make in such a way that this geometry is Minkowski, and you get an effective action for linearized perturbation like this. Now this seems something that has nothing to do with gravity, but then let's do the intuition of the Bose-Einstein. I do a kind of modeling representation, a common amplitude and a split in phase, these perturbation fields. And I have this set of equations, and now look at some magic. You introduce a conformal metric, conformally flat metric, and you can rewrite everything, including a Ricci tensor, in this way. You know this theory, what it is? This is Nostrum gravity. Again, there is Domenico there that I feel explaining Nostrum gravity. So it's basically this is to me is one of the scalar theory of gravity and no vector, in the sense it was an attempt to create a scalar theory, a relativistic theory of gravity, because between, say, special relativity and general relativity, this is the so-called Einstein-Fock equation. And you see, what we recover is basically Nostrum gravity, which is the most you can get in scalar theory. So, note that here, matter and gravity emerge at the same level. So, matter and gravity are two sides of the same thing. Another lesson, this other personal guess is that you cannot expect to emerge gravity without emerging the standard model. I find very difficult to imagine that everything, the two things are not related. In scalar tensor theory, it's very difficult to separate what is gravity and what is not, for example. Anyway, this is the conclusion, and I want to stress that this equation, in a limited sense, is also different variances. Because it's true that there is a prior structure, the Minkowski metric, but basically the initial equation, this one, is a conformal invariant. So at most you have as a background structure you can access for this kind of matter that is in this model, is the conformal structure of Minkowski. So here it is another example where even the Fromer field invariants emerge. So this is the end of my talk. I just stress that all of this works for linearized perturbation. You go to the next order, and Lorentz and the different variants are broken. There is no, it's again, they are both accidental symmetry. This is the next order in the perturbation theory, and you see that breaks everything. And this is the conclusion. So what we have learned? We have learned that there are basically, from this Lorentz model, 3 points where we can look for. One is well known, Lorentz violation. And I made a personal guess that if you don't emerge everything at one step, you really need Lorentz violation in the game. Secondly, and this is my Kildor proposal because Lorentz violation is very strong cosine. Secondly, there are these UV non-locality effects which I would like to know if they can give a low energy observable. And third, you may expect as well background independence to be broken at high energy, because there you have to go next order in perturbation theory, which is equivalent to high energy. And this is where we stand in this particular way of line of research, and this is where we try to advance. I hope the next meeting to report something new.
The last thing I heard about these attempts, you and Matt were working on this Bose-Einstein condensate with two types of particles, trying to obtain, and you managed to obtain the two fitting the same method.
Yeah.
But my question is, what happens to that once you introduce interactions between the two particles? Because that's how we got the problem.
No, but the interactions are really there because they are at the next order. We haven't computed the see. This is a very good question, and let me try to clarify. We were studying this model with a 2BC exactly because we wanted to see if there was a solution of the Turner's problem in an Reynolds model. And we found out that the dispersion relation was exactly of the things we were hoping for, which were a suppression factor. We were setting the two phonons in such a way that they had the same speed of light at low energy. This is basically done by setting the microscopic quantity. It has nothing to do with the life of the phonons. It's really that the microscopic system must have some symmetry. Okay? Now the phonons have the same speed of light at low energy without Lorentz breaking. Then you switch on Lorentz breaking by taking into account the quantum potential, and you see if it induces a coefficient in front of the p squared. And we found out that the coefficient was the mass of the phonon divided by the analog Planck mass squared, which is the kind of suppression you would hope for in order to solve the naturalness problem. But our calculation was not an effective theory calculation like the one I've done. It was ab initio. We were deriving from the microphysics directly in one step of what was the dispersal relation, like I did also here for the single phonon. So I would like to do, and this I think is something that needs to be done, to go the next order. I have also the vertices. There I can do the effective field theory calculation. It's more complicated. I cannot do it at the same order at which I did the one. And I want to see in the effective field theory case what happens. But personally, Daniel, if you want my opinion, if there is a serious solution of the naturalness problem, it's not going to come from a custodial symmetry. I start to convince myself that there is another possibility. And you see, the naturalness problem of the cosmological constant is teaching us something which may be profound, that there are some questions where the effective field theory fails. Maybe that the naturalness problem for Lorentz violation has to be treated in an analogous way to the one for the cosmological constant. And though I don't know now, in this moment, I've been thinking about it, but I didn't come up yet with an idea how to do that.
So just a little comment, maybe it's not relevant, but about this, which I would make a distinction between, maybe it's not relevant, but about the inspiration that you might draw what you get for the cosmological constant and the higher order operators that you have for Lorentz violation, which is the difference between this failure of the inspiration from effective field theory. The point is that for operators like the cosmological constant or the terms like the mass of the Higgs, those are relevant operators, and the corrections that you get there are dominated from the UV. So in a sense, it's not so much that effective field theory is failing. There, the point is that it's coming from the part that you really don't know. So in
that sense, I was saying, you see, the idea of effective field theory is also that there are basically all the relevant quantities for your low energy work can be computed with the physics that you do up to the cutoff. In a certain sense, there is exactly telling you must know all the microphysics to get to the right answer.
No, but I would say that in a sense, the relevant quantities, they are very sensitive to the UV details. So in a sense, when you do effective field theory, you would just do measurements and fix them. So they are very unstable to relative corrections. But what I'm trying to say is that those are very different from the irrelevant ones in the sense that they are very sensitive. They get lots of corrections from the UV sector that you don't really know a lot about, that you don't know anything about. Whereas those that are irrelevant, those get a lot of contributions from the infrared sector that you don't know, you do know the details. So what I'm trying to say is that I think that there's a significant difference between what you get for the cosmological constant.
No, that I agree, because otherwise I would have that I realized. The point is that my point was simply for the cosmological constant. I don't understand if you're trying to make the point that I can compute the exact result without knowing the Hamiltonian for the atoms, which is a much larger object than the Hamiltonian for the phone. I mean, that is like it's knowing, if I know only the Hamiltonian for the phonons,
you cannot. There you need the microscopic details. But what I'm trying to say is that I'm not sure that the inspiration that you can get from the cosmological constant can be applied to the relevant operator.
But what I remind is that in order to understand, that means that somehow to calculate the modified dispersal relation, including all the terms, could have been protected by some symmetry which is not of the effective field theory, but which is of the fundamental prosthetic.
Yeah, so I like everything you say except the stuff about emerging diffeomorphism invariance. Yeah. So let me explain why I'm skeptical that emerging diffeomorphism invariance is like emergent getting-Mills gauge invariance, and maybe you can explain me. So there are models like when and collaborative Levine and where gauge invariance, ordinary gauge invariance is emergent. And it's not difficult to understand what happens. What happens is to make ordinary gauge invariance emergent, you have to suppress the longitudinal mode of the vector field with respect to the transverse modes. But given that the longitudinal mode is a scalar mode, and given that there's a mass scale, which is the cutoff scale, it's natural to have the longitudinal mode suppressed by the cutoff scale and not the transverse mode. So one gets a gap between the longitudinal mode and the other way, longitudinal mode and transverse mode. And one can have at low energies effectively just the transverse mode and therefore have emergent gauge invariance because the Gauss's law is effectively acting on the GTD couple, the longitudinal mode. But the same argument, to my knowledge, has never been made to work in the spin 2 case.
Okay, this is spin 0, this one. And I'm not sure that anything like this can happen for spin 2. I want to be clear about that. I'm not overselling you this result. This, moreover, is a limited. Remember that for example, you know that in non-strong gravity, if you try to compute an Nether charge, you get basically an indefinite result. We tried with Florian after. What I mean is that my impression is that this should be taken as a kind of circumstantial evidence, no more, that maybe there is something you can do in the sense of emerging diffeomorphism invariant. But I do think that non-strong gravity is a very special case in this case. It's a kind of limited background independent. Concretely, you know, there is a background field, which is the Bernoulli geometry there. So there is in a sense, this is why I made the comment about the fact that just because you have the special content of matter, which is conformal invariant, then only the conformal group of Minkowski's what you really can access, is very special to this model. Sincerely, I don't think that anything from this can be generalized to spin 2.
I have two naive questions. I asked them.
You will get two
naive answers. Okay. Yes. So first, if space-time is emergent and you treat it as a thermodynamic state, then there is no really motivation to quantize gravity.
Right. Oddio. I'm not that. What I mean is that look at the hydrodynamics. It's not that working with phonons is totally useless. Or I think that there are. It's simply what you want to get from it. That you must be aware of your limits in a sense. So I wouldn't say that you have to throw in the garbage the stuff we have done in semi-classical gravity or radiation from the when we are trying to do steps to work quantum gravity. That is not a priori. But for example, you shouldn't be so much scared by the fact that when you go beyond linearized gravity and so on, quantum gravity, you get into trouble and so on. It's not. There are things that you can do with that theory and others that you can't. It could be a very useful theory.
Okay. So, and the second one is, you said that you stressed there is a kind of detachment between the two principles of relativity, the principle of relativity and the principle of constancy of light. And yet, in the violation of one need not lead to the violation of the other. And yet, here, it seems that, as a matter of fact, both are violated, or both are supposed to be violated in the ultraviolet regime. So, is this a coincidence, or it's not something necessary?
No, I don't think so. I mean, here we were looking at a particular set of simple models. No? What I just wanted to stress is that somehow the constancy of the speed of light, you can get when you go from special relativity to another special relativity group. Of course, at the speed of light, at some point you will go from speed of sound to speed of light. And let me stress that there is another complication. You are going from phonons to atoms. It's not just that the dispersion relation change and that the limit speed change. You also are passing from collective excitation to Costello. I don't have a definite answer. I don't know how to answer in a sharp way. It seems to me that a priori there is a link, in the sense that I hope that there could be even another, you can say the relativity principle. I don't like the idea that the fundamental word actually there is given in a preferred system, personally, but this is, of course, is personal opinion. But, so I would like to have a way to preserve the relativity principle, implement it in a new way. And for example, even with Euclidean Poincaré, I like very much the idea that maybe that the fundamental system doesn't even have time. Sorry. Oh, any questions?
Well, I'm afraid we publish. Okay, 2 more questions. You work yourselves out now.
You work yourself.
quick. Okay. Very, very brief. since you kindly mentioned the non-critical strings and you constrained the model, I would like to make a more general comment on the special relation and how we evade the constraints with a corrected version of the model of ours in 2001. What we missed in the model of one was that when we wrote down the special relation, the modified on average, we did not take into account the microscopic model of the interaction of the string with the defect. And then the psi parameter that enters in your formulas for the modified had correction. So in other words, there is a coupling that is Finsler type as well. In other words, the strength of the interaction, and that is actually a general comment which might actually be characterizing the special relations, depends on the momenta in such a way that you have, let's say, energy over M Planck, the corrections, but there is 1 minus energy square over M Planck square, which is a velocity. The recoil velocity of the d particle, because string theory is respecting event invariance on a fundamental level, is always less than 1. What we missed, much to my disgrace, to our disgrace, is that the V can never exceed 1. Therefore, when the energy approaches the GZK cutoff, which is the string length, whatever, the interaction strength vanishes. So the dispersion relation is not modified above that. And then we are back to the normal where you don't have the, you cannot have gamma-gamma interactions or whatever. So my comment, and I'm finishing, is that when people write modified dispersion relations, the parameters psi, naively in effective field theory, sometimes you may have momentum dependence additional ones, which if they are of the type 1 minus u squared, they introduce horizons in the metric, in the Fischler metric. And the horizons in the Fischler metric invalidate the weak gravity approach, and that's why you get misleading results. That's all.
Yeah, I think that anyway is an interesting exercise to realize that it's not true that you can constrain only effective field theory.
Yes.
I mean, depending on the theory, even if it's not satisfying effective theory, there are you are sufficiently careful. There are windows of opportunity. Let me just remark that a model should have more than a windows of opportunity to be. If you only have one kind of observation you can do, I think it's weakening the model. I would like to have a model that can be constrained in different sides.
Yeah.
So I think that, for example, for the last version of your model, it's very important to keep looking for something different from the time flat.
Precise. Absolutely.
Okay, one last question, which I believe is that maybe Faye, we could start setting up.
In the context of constant gravity, did you look at the real Klein-Gordon equation?
What? The real Klein-Gordon equation?
Or didn't you look at the Klein-Gordon equation for getting constant in this slide?
I'm not sure I understand what you're talking about, but in the sense that we had a Klein-Gordon equation, of course.
Here.
Now, the fundamental equation is this. Well, basically, this is the fundamental Lagrange. We do this ansatz, this kind of, we call it an analog of the Madelung representation, where the amplitude time phase, with the phase are constrained to.
So the phi is a real number or?
Yeah. And it's nice when you answer the question without really understanding.